So in this 50th lecture, I'll start with another kind of full wave rectifier, that is a bridge rectifier. This type of rectifier that we'll discuss today is a bridge rectifier, initially with the circuit diagram and the working of it. Now again, first of all, it comprises of a transformer. Very first thing that you have a transformer here. It can be a step up or a step down transformer, but I am showing a step down transformer here. This is a step down transformer here. It is a step down transformer. And we use 4 diodes here. I'm using 4 diodes here. How these are connected and what is the working of this? This is the first diode, suppose I say. First diode is this. Here. From this point itself, I'll use another diode. This is the anode of this diode, and here I show the cathode of this diode here, and connected here at this point. Then you have another diode, third one, with anode at this point and cathode here, and the fourth diode which I connect here between this and this. Suppose I say that this is the case here, and here I apply the load resistance RL. This is the load resistance RL of the circuit, and of course this transformer is connected at this point and at this point. Assuming this to be either a step up or a step down, although I have shown a step down because as I am showing, the number of turns in the secondary are less than the number of turns in the primary. So this is the very basic circuit of this bridge rectifier. This type of circuit is called a bridge rectifier. And suppose now I name these diodes. Suppose I say that this is diode D1. I name this diode as D2, this diode as D3, and this diode as D4, and this is the load resistance RL. This is a transformer having any turns ratio. This turns ratio of this is, suppose, N1 is to N2, and if I apply a voltage, a supply voltage Vs here, and AC voltage is applied here, which is equal to Vs, which is being either step up or step down by this step up or a step down transformer, and the input voltage is the voltage at the secondary of this. The voltage which I obtain at the secondary of that, I assume this as input voltage as Vi. This is the input voltage Vi, and whatever I'll derive is with respect to this Vi. With this treating this as an input voltage means from here the rectification will start. Of course, this transformer is used to either step up or step down the supply voltage from here. So these are the 4 diodes, and I assume these diodes are identical. Each one is having a forward resistance RF. That is, this is also having a forward resistance RF. This one is also having forward resistance RF. This is also having a forward resistance RF, and this diode is also providing a forward resistance of RF ohms, which is of course very less as compared to this load resistance. So this is the circuit diagram of a bridge rectifier. Now let's see the working, how it works. That is, initially I say that this is Vi, which is a sinusoidal voltage. I sketch this voltage here. Suppose this is my input voltage Vi. I draw this Vi. Say this is of course omega t on this side, and this is input voltage Vi. I assume this input voltage Vi, which is of course a sinusoidal voltage, a voltage which is sinusoidal in nature, and this is the input voltage. I hope this is clear to you. The points, this is omega t, 0, pi, this is 2 pi, 3 pi, 4 pi, and so on. and I drop down these points here. I simply drop down these points here. These are the same points. That is pi 2, pi 3, pi 4, pi and so on are dropped down here. And let's see what will the output voltage or output current. I sketch this output voltage or output current here. Of course, this is omega t again. This is omega t. Now, look at this. What happens that during the positive half cycle, I'll say that during the positive half cycle of input signal, during the positive half, suppose I say that this point is A and this point is B. This is A and this is P. During this positive half, let's take case 1. Case first. That is, during the positive half, when omega t is between 0 and pi. Case first. During positive half of Vi. During positive half of Vi implies that when omega t, I'm saying when this omega t is between 0 and pi. Now what will happen under this condition? If you see, that is when I say this implies that A is positive. I say A is positive with respect to B. This point is positive with respect to B. Now I am showing with the help of pencil here so that I can rub it. This is positive and this is negative. This B is negative. This is positive and this is negative under this condition. Now what will happen? Just see. This D1 is reverse biased. It is this cathode is connected to positive. This D3 is forward biased. Again, this is connected. This anode is connected to negative. So this is reverse biased and this is forward biased. So I can say that this D3 and D4 are forward biased. So D3, if you see, look at this. This diode is forward biased, and if you see that this diode is forward biased. So D2 and D3 are forward biased. On the other hand, this D1, since this anode is connected to cathode is connected to positive, so it is reverse biased, and in this case here this anode is connected to negative terminal, so it is also reverse biased. So this implies that I can say this implies that D1 and D2 are D2 and D3 are forward biased. D2 and D3 are forward biased. These two are forward biased, and the other two, D1 and D4, are reverse biased. D1 and D4 are reverse biased. I hope that this point is clear to you. Now, when these two are forward biased, they will act as a closed switch, and these two will act as a open switch. So I am drawing this figure once again here. That is, you have this circuit something like this. Let me draw this again. This is the first case. This is the case. Look at this. What will happen? This will act as a open switch. These two diodes are acting as a open switch. First of all, these two are acting as open switch. This is point A and this is point B here. This is acting, this one is open switch, as well as this is acting as a open switch. This is acting as a open switch. On the other hand, this will act as a closed switch. If you see, this diode will act as a closed switch, of course offering a resistance RF, this diode. And similarly, this diode D2 is also acting as a closed switch. It is acting as a closed switch and offering a resistance RF here. This is also offering a resistance RF, and of course you have this load resistance RL here. Now what happens? Just see. These are these two terminals here. This terminal, this terminal. Current, remember that it always flows from anode to cathode. Now what will be the direction of the current if you see in this case? From here, the current will have two paths from here. The current has two paths, either this path or this path. It will always follow the low resistance path. So this is the lowest resistance path. There's no connection here. So the current will flow in this direction. Let me show with some other color. So this is the direction. The current will flow in this direction. Here, then it will in this direction. Again at this point, it has two paths, either this path or this path. It will follow the minimum resistance path. Of course, it will be this path. It will follow this path. From this point, again it cannot move in this direction, so it will move in this direction. And further, it will not go in this direction, but the current will flow in this direction. And this will be the direction of the flow of the current in this direction across this load resistance RL. So this is the situation when this A is positive with respect to B in this region, either in this region or in this region, I can say. Of course, it will follow the input current VI, where the instantaneous value of this VI, I assume this as Vm sine omega t, means this is Vm. This is Vm. Now the current that you obtain here, suppose I say that this is the output current I across load IL or IO, or in simply it is I. So it will be like this. And of course, the value of this current will be Im sine omega t. If you see, the current which will flow is Im sine omega t. So the current I in this case will be Im sine omega t. Let me write here. The current which will flow, I, output current, means this current I am talking, it is equal to Im sine omega t. Let's talk about the second half, case 2. I am writing here only. Case 1 as well as case 2. I'll make changes here only. Case 2 means during the negative half cycle of the input. That is during the negative half cycle. In spite of positive, a negative half cycle of this much, when omega t is varying from pi to 2 pi. I say it is from omega t is between pi to 2 pi. Pi to 2 pi means when A is negative with respect to B. Now in this condition, this terminal is negative. I am saying positive or negative with respect to A. So during this side, when this cycle reaches here, this side, now this will become negative. It means now this is negative and this is positive under this condition. This is negative and this will be positive. Now what will happen? Look at the condition of the diodes. What will happen? This is negative, this is minus, and this is plus here. Which diode will be forward biased and which diode is reverse biased? That we have to see. Now if you see under this condition, this negative is connected to anode, it means that this diode is reverse biased. This cross means I am saying that this is reverse biased. And look at this. Of course this diode will be forward biased. D1 is forward biased. Look at this terminal. This D4 will be forward biased and this D2 will be reverse biased. So D1 and D4, if you see D1 and D4 are forward biased and D3 and D2 are reverse biased. So D2 and D3, under this condition, D2 and D3 are reverse bias and D1 and D4. Look at this D1. Negative is connected to cathode. This D4. Positive is connected to anode. So it is forward bias. So I can say this D1 and D4 are forward bias. So it is very clear that D1 and D4 will act as closed switch and D2 and D3 will act as open switch. These two diodes will act as open switch and these two diodes will act as a closed switch. So let me redraw this figure. This is the figure for the case when omega t, this is for positive half cycle, when omega t is between 0 and pi. Second case I am drawing here, that when omega t is between pi and 2 pi, that is for the negative half cycle. Let me draw this figure again. Say this is the situation. Of course, this is the load resistance here. What will happen? That D1, this is forward bias. D1 and D4 are forward bias. I am showing with red pen only. So this is forward bias, means this will act as a closed switch. this will act simply as a closed switch, of course offering a resistance RF. This offering a resistance RF. This one, this D2 is also, D2 is reverse biased. D1 and D4 are forward biased. This D4 is forward biased. I show that this D4 is forward biased. This D4, if you see, again it will act as a closed switch offering a forward resistance RF. And of course this one will act as open switch, and this is also acting as a open switch here. This is the situation. This is the load resistance RL. This is the load resistance RL here. Now see what will happen. Again, these are the two terminals here. Now look at this. Current will always from positive to negative. This current, look at this point. This diode is forward biased. From here, the current starts flowing from this direction. Suppose I say, I'll show it here. The current is starting from this side, from positive. This side, it will follow this path. This current I'm starting it. It will follow this path, of course. It will follow this path because here it is open. Again, at this point, it has two paths, but it will follow the minimum path in this direction. Further, at this point, it will not go this side, but it will go towards this side. Again, at this point, the current will not take this path, but it will take the minimum resistance path. And this is the overall path of this current. Now look at this, the point to be observed here. Suppose I say that this point is P and this point is Q. Although the polarity has been reversed in pi to 2 pi, initially polarity was this was, although the polarity is reversed, but if you see that across this load, the direction of the current is P to Q, whether in this, it is in this direction, and here also it is in the same direction. So the output current, it follows in this also. This is 0, pi, 2 pi, 3 pi, and so on. So the current is flowing in the same direction. For positive, again it will be the same thing as I repeated here. For negative, same. So this is the case for omega t between pi and 2 pi. Here D2 and D3 are forward biased, and in this case D1 and D4 are forward biased, and rest 2 are reverse biased. So this is, we can say that this, the full wave has been rectified here, and this is the working of this. Now the point that we have to see in this case, we said that the output current, this I, input voltage is this. If Vi is equal to Vm sine omega t, what is the output current I? I am saying that this is your output current. Output current I said that the instantaneous value of this current, of course it is equal to Im sine omega t. Value of this is equal to this much. Im's instantaneous value is Im sine omega t, and this we say that this is Im. Now this Im will occur at V is equal to Vm. Now if you observe this, suppose I say at any point this is Vm. Suppose I say this is Vm. Current flowing here is I. Suppose I say when it is Vm, current will be Im. What is the value of Im? It will be Vm upon Rf plus Rf plus RL. Initially it was Rf plus RL. Now it will be Vm upon Rf plus Rf plus RL. Look at the complete circuit. If I put a battery here, look at the total resistance here. It is Rf plus Rf plus RL. So I is equal to Im sine omega t. Sine omega t. Of course, omega t is varying from 0 to pi, and the value of this pi, of this Im, which is the most important point here, the value of this Im is equal to, Im will occur at V is equal to Vm. It is equal to Vm upon Rf plus Rf, means 2Rf. 2Rf plus RL. I hope that this is clear to you. This point. It is equal to In the previous two rectifiers which we have done, Im is equal to Vm upon Rf plus Rl, but now here it is Rf plus Rl, so it is equal to 2Rf plus Rl. I am assuming that all the diodes are identical. So this is the working of a bridge rectifier. I'll continue with this in the next lecture. So thanks for the time being.